So we started this unit off by talking about the four fundamental forces of the universe, and we focused in on gravity. And we know the formula for a force of gravity is G m1 m2 over r squared. And we talked about that formula because there's a lot of connections between how it looks here and then the force of the electric field. Both have a constant. With gravity it's G, with electric field it's K. Instead of looking at mass, we're looking at charge in this case, but in both cases, we're looking at how far away the two objects are. Then we talked about, with forces, we eventually derived the formula of energy due to gravity. And we discovered that it was going to be negative G m1 m2 over r. So why was it negative though? Well, let's look at here. We're going to draw our picture of Earth, and here's going to be you. Okay, now if you're floating out here somewhere in space, but you're within the sphere of influence of Earth, we know an attraction is going to occur. Because an attraction is going to occur, it's going to force you to go down. That's why we had a negative value here. That logic is going to be important in just a moment as we talk about the energy as a result of an electric field. And what that is it's going to be K Q1 Q2 over R. Now note I didn't put a negative here. Should I? It depends on the situation. We're going to use some common sense, and let's talk about this. If we have, let's say, two positive or two negative particles, and I take this positive particle right here, and I bring it closer. Well, what I'm doing in that case is I'm storing energy. And the moment I let go of my force, what is this going to do? This is going to go out this way. We know that'll happen. So if I was to try to graph this, and we compared, let's say, energy, with this being positive and this being negative, versus distance away. Well, when I'm taking this particle, and I'm bringing it closer, I'm storing more and more energy. And when I let it go, I'm letting that energy go. So I would argue this graph is going to look something kind of like this. And that's going to happen because as we get closer and closer, we know we're storing energy to do something. Let's look at the opposite. Let's say instead I have a positive particle and a negative particle. Well, if I was to take this and just leave it right here, it's naturally going to want to attract back inwards. So it's going to lose energy. So it's not like we're storing energy. We know if they're close, they're going to want to attract together. So if we go ahead and we do the exact same graph like we did up here, with energy versus distance, we're going to see the opposite happens. So as the object gets closer and closer, it just naturally wants to get closer, so it's losing the energy in there. So whether this has a positive sign or a negative sign is all dependent on whether there is attraction occurring or repulsion. If attraction is naturally occurring, it's a negative. So if we think back to grade 11 chemistry for a moment, we learned about potential difference, or electric potential difference. We called that V. You know this as voltage. And the formula we learned last year was looking at how much change in energy there was per unit charge. Now we established from up here what E can represent. So if we go ahead and we plug this in, we're going to end up with KQ Q over R over Q. And automatically, we can sort of cancel out two of these Q's. And what we're going to be looking at eventually for voltage is K Q1 over R. Now, R refers to the particle we have of interest. So it's like our test charge in this particular case. And what our units will end up being will be joules per coulomb, which we also know as a volt.